Exploring the Solar System Part 2, how we explore the solar system with spacecraft. So I'll be asking the questions, how do we get there? What do we do when we get there? How do we get images back if we do decide to go out and start exploring planets in the solar system? And again, the question is, well, what happens next? I thought I would look back when I started writing this, again, short talk as to, well, what's happened over the last 70 years, because we've of course been sending spacecraft up for quite a while now. How many spacecraft have we sent up? And the answer is, well, quite a lot. And this needs updating because I've got Europa Clipper as the last thing on this list, and it really ought to be Artemis 2 as the last thing on this list. So yes, we have sent up hundreds of spacecraft to explore the solar system one way or another. And the question is, how do we do that? Let's first think about how we explore, for instance, Mars. I've been talking about robots on Mars, but how do we get from a planet going around the sun, like the Earth, to a planet like Mars? This particular diagram is quite definitely not to scale. If we wanted to go from Earth to Mars, we get there via an elliptical orbit called a Hohmann transfer. And that's it, separated from the Earth orbit and the Mars orbit. It's an elliptical orbit around the Sun, where the shortest distance to the Sun is the same as the Earth-Sun distance, and the longest distance from the Sun is the Mars-Sun distance. So if we can get from the Earth orbit into that blue orbit, then we can effectively go from the Earth to Mars. It's not quite as simple as that blue diagram would indicate, because it looks like if you head off to Mars and decide not to land, then you simply continue on the blue orbit and end up back at Earth. But bearing in mind how long it takes the Earth to go round the Sun, 1 year, and how long it takes Mars to go round the Sun, 2 years, the blue orbit, the so-called Hohmann transfer, the elliptical orbit, takes about 1.5 years. So if you go from the Earth to Mars and decide not to land, you do indeed end up coming back to Earth orbit, but you end up coming back here 1.5 years later. And of course that means Earth isn't there anymore, because Earth will have travelled 1.5 of an orbit around the Sun, and so the Earth will now be approximately where the cursor is rather than where you left it. So going to Mars is problematic. It's the easiest orbit to get into, but you do have to worry about the timing of when Earth and Mars are in the right place. Notice that you leave Earth and arrive at Mars when they are on opposite sides of the Sun. Seems a little counterintuitive, but actually that's the most fuel efficient way of getting from the Earth to Mars. When it comes to other planets in the solar system, well, it was realized back in the 60s and actually implemented in the 70s that you can use a gravity assist. Here we see a spacecraft passing Jupiter and getting an extra kick, which gives it an increase in velocity and sends it on, in this case, to explore Saturn. This was the trajectory of Voyager 1. I can run that particular animation again. Whoops, run that animation again so we can see it. The spacecraft leaves Earth. The spacecraft is the purple. As it encounters Jupiter, it gets a kick and a dog leg kick to the left, increases its velocity, and then goes flying off for an encounter with Saturn. As long, again, as the planets are in the right place, you can get this gravity assist, which sends you to the outer solar system faster, and you use less fuel, which means you can ultimately, for a given amount of payload, you can take more scientific equipment with you. So this was realized in the 60s, and that's why Pioneers 10, 11 and Voyagers 1 and 2 were launched in the 70s to take advantage of an alignment of the outer planets. Voyager 2 actually took it beyond Saturn. It got a gravity assist from Jupiter, flew on to Saturn, and then got a gravity assist from Saturn, and then flew on to Uranus and ultimately Neptune. So it did essentially the grand tour of 4 of the outer planets for effectively no additional cost, because once you had launched from Earth, apart from a tiny little mid-course correction, you didn't need to fire the engines again in order to accelerate from one planet to the next. The gravity of one took you on to the next one. This idea of a gravity assist or a flyby or a slingshot, call it what you will, is a very useful way of exploring the outer solar system. It's actually also used for the inner solar system as well. Bepi Colombo is on its way to going into orbit around Mercury, and it's been using gravity assists from the Earth and Venus and Mercury itself before finally going into orbit a little bit later this year. One of the first images obtained of another world was this one. I'm not sure if anybody recognizes this. If you had to guess which world it is, well, if I told you which spacecraft obtained this image, you would then know, because this was taken by Luna 3. So clearly this is the moon, the far side of the moon, taken in October 1959. And of course this will be seen again by our plucky astronauts who hopefully will be launching in just a few hours on Artemis 2. We can get rid of some of the noise here and see that, well, it's a relatively low resolution image. And all we can see is a few splodges of dark areas and light areas. But let's remind ourselves, this is the 1950s. This is before digital cameras existed. So how was this image of the far side of the moon obtained? Well, it was on emulsion film, standard photographic film, before the days of CCD chips, etc. So the film was exposed, and then the film was developed in a little chemical laboratory on board the spacecraft, and then it was fixed and then dried. Then it was scanned by a cathode ray tube, a flying spot, projected through the film onto a photomultiplier that recorded the brightness levels of various parts of the image. And the signal from the photomultiplier was then transmitted back to Earth on a radio signal, and that allowed people on Earth to reconstruct the image, much like a fax machine takes a digital signal and then reconstructs an image from that. With apologies to any youngsters who don't even remember what a fax machine is, let alone what film emulsion was. If we compare it with an image taken half a century later from the NASA Lunar Reconnaissance Orbiter, we can see that although the LRO image is of course much higher resolution, notice that all the features are basically right. The dark areas and the light areas have been faithfully captured by the film, and then ultimately the process by which that information was transmitted back to Earth. But of course it wasn't long in the early 60s when people realized this is not a way we can continue to image the planets that we want to explore. We need a better way of getting the information back to Earth rather than using film, developing it, scanning it, transmitting the intensities back. So in the mid-60s we had the Mariner probes, and Mariners 4 and 5 had the world's first digital cameras. Not the first digital cameras to be used on spacecraft, no, I mean the world's first digital camera. So for those of you who've got a digital camera in your mobile phone, the pedigree, the provenance effectively goes all the way back to the Mariner spacecraft of the mid-60s, when it was decided we want to be able to use CCD technology to actually take the light and convert it directly into intensities which we can then transmit back to Earth. So as the Mariner probes flew by Mars, they recorded the images they were taken on the digital camera. These images were recorded on tape. After the spacecraft had flown past Mars, then the tape was effectively rewound or read and transmitted back to Earth. And then again, the digital information was then reconstructed into images. So this was mid-1960s. Again, we can take that original image and we can clean it up a little bit to remove the noise, and then we see very clear features like craters, etc. on the surface of Mars. So digital imaging came of age a few years after film was tried, and of course we've been using digital imaging ever since. We've now explored essentially every planet of the solar system and quite a lot of the other bodies in the solar system, including minor planets, various asteroids and moons, etc. Let's just have a quick look at one of those missions to, in this case, Saturn, the Cassini mission. I'm not going to talk through all of the details. All of this information, of course, is available on the NASA web pages. But simply a reminder that as well as travelling billions of miles, the interchange between what's going on at mission control and the commands that are sent to the probes, in this case, millions of commands were sent from Earth to the probe to tell it what photograph do you take next. In other words, are you going to be pointing at Saturn, or are you going to be looking at Saturn's rings, or are you going to be looking at some of Saturn's moons? It took thousands and thousands of images over its life, from 2004 until when it was finally crashed into Saturn in 2017. It was crashed into Saturn simply because it is thought that some of the moons of Saturn could conceivably harbour life, and therefore, rather than risk the possibility that leaving it in orbit around Saturn might crash it into one of the moons, it was deliberately crashed into the surface of Saturn. In the bottom right, you can see the scale. These missions, these spacecraft, are by no means small. It's almost the size of a house, basically. And sitting on the side is the Huygens Explorer, which we'll come to in just a moment. If we remind ourselves what we can see of Saturn from the Hubble Space Telescope in Earth orbit, if we think about what the detail we can see in the rings, it might be rather impressive to see what we can see with Hubble, but that bears no resemblance to what we can see when we get closer with Cassini. We can now see a huge amount of information, and the rings start to resolve into not just a few, but in thousands, tens of thousands, hundreds of thousands of individual ringlets. Starts to look like a long playing record. Again, with apologies for those who don't remember what a long playing record actually is. The ring system is extremely flat. It might be 250,000 kilometers or so in diameter, but in some places it's thought to be a thickness that's only measured in meters, at most a kilometer or two. When the sun is in the right direction in the ring plane, coming in at a very shallow angle, you notice that it can sometimes cast shadows. Here you see shadows of what appear to be bumps coming out of the ring plane. Most of the rings are extremely flat, but some of the rings appear to be very bumpy and cast these shadows of these mountains. The bumps aren't huge, the bumps might be only kilometers or so in height, but trying to understand the structure and the dynamics of these things helps us understand the dynamics and the origin and the evolution of the rings themselves. One thing that Cassini can do that is not possible from Earth is to fly into Saturn's shadow and see the rings backlit. We can never see that from Earth. We can only see the rings lit from the sun. Because the Earth is relatively close to the sun, we always see them front lit. But Cassini was able to fly into this position, and so we can see a little bit of light coming through the Saturnian atmosphere, but the ring system is lit up from behind. This is very valuable to scientists because when you have a ring system like this, remember the rings are not solid, they are trillions of tiny icy particles. But just how big are these particles? By looking at how sunlight is scattered when the sunlight is coming from behind, this so-called small angle scattering allows scientists to start to get an idea of how large these individual particles are. Again, it gives us a better idea of the evolution of the Saturnian system. Huygens pitched a ride. There's Huygens sitting on the side of the spacecraft that I noted earlier. And Huygens was a probe that was sent in to the atmosphere of Titan. Titan has got such a thick atmosphere, despite being only a moon, not a planet. It's got such a thick atmosphere that we really can't see the surface at all. And so the Huygens probe was sent in on a parachute and videoed or took images on its way down to get an idea of what the surface of Titan actually looked like. because up to this point it was all guesswork. As Huygens plunged into the atmosphere, it saw a landscape, and the landscape was much more varied than we appreciated. It has mountains, and it has lakes, and it has rivers, and it has clouds, and it has rain, much like Manchester, basically. But it's clearly a world very different from, for instance, our moon. Because it has a thick atmosphere, it has dynamic processes that are very different from the relatively sterile world of our own moon. And remember, I said in the last talk, there are plans to send a helicopter to this world so we can explore it in more detail. As well as exploring Saturn, we've spent a lot of time exploring Jupiter, and here's the Juno probe that's coming towards the end of its life. It arrived in 2016. It's had something like a 10-year lifetime. It was due to be decommissioned in 2025, but I think, to the best of my knowledge, it is still operating. It's in a very harsh radiation environment, so it may not last much longer. But again, I'm not going to talk through all of these numbers, but again, it's travelled for billions of miles. It has accrued huge amounts of scientific data, some images as well as measurements of the magnetic field and the radiation environment, as well as information from the various moons as well. Here's a flyby. It doesn't spend all its time close to Jupiter because it's a high radiation area, but it does swoop close to the Jupiter's cloud deck. And here we see the intricate structure of the clouds. The white flashes that you can see there are lightning flashes. This is a time lapse. It might take a few hours, and it's been compressed in a minute or so of this video. So it swoops over the cloud top and then, in a very eccentric orbit, pulls away from Jupiter. You can see some storm systems there. You can see the colours. There's clearly a lot of contrasting colours that are visible, and that is telling us something about the chemistry. The rather orangey colours are probably the result of minerals containing probably sulfur and phosphorus. And when we look towards the poles on the left-hand side of this image, there seems to be a lot more bluish colours. So there's definitely large variations in colour, as well as variations in the structure of the clouds themselves and the storm systems that we are still trying to understand. Why is it that storm systems seem to rage on Jupiter for hundreds of years, whereas storm systems on Earth tend to peter out after a few days? What is it on Jupiter that drives storms to exist for hundreds of years at a time? Again, perhaps understanding the storm systems on Jupiter might help us understand some of the chaotic nature of the weather on Earth. When we look in detail, this is a snapshot of what Juno saw when it skimmed over the cloud tops. Yes, it does look a little bit like a watercolour that's been left out in the rain. And people are trying to understand that central dark spot, for instance. That appears to be perhaps a vortex, in the sense that it's a deep chasm, and we're looking into the planet. We're looking to lower parts of the cloud deck. But again, understanding not just the two-dimensional structures that we can see here, but understanding the three-dimensional structure of the various cloud layers that exist, each of which probably has different minerals, different temperatures, different pressures, and perhaps different circulation of the various clouds. Trying to understand that as a three-dimensional problem is still quite a bit of a challenge. But the solar system is not just the Sun and the 8 planets with which we are now familiar. New Horizons has explored Pluto and is now exploring what is beyond Pluto, the Kuiper belt, which is a large belt comprising lots of icy bodies, some of which are quite interesting. New Horizons hasn't got the ability to go exploring by steering towards the objects, but hopefully there's enough interesting objects out there that as it leaves the solar system, it will pass some of these, and its power supply, a bit like the rovers I was mentioning earlier. It has a thermoelectric generator as a power supply, which hopefully should keep it going for 50 years or so, and if it's lucky enough to pass some objects in the Kuiper belt, it will be switched back on to see what information it can learn from these objects way beyond the orbit of Pluto. And of course, it's not just the planets. There are also 300 moons in the solar system, some of which are very interesting in their own right. Here's just a tiny sample of them. Some are quite small and look a little bit like potatoes. Some are much larger and look almost spherical. Some look like pizzas. Some look like the Death Star from Star Wars. And there's Titan with its hazy atmosphere where we can't really see what's going on. And there appear to be walnuts and other weird and wonderful shapes as well. There's our familiar moon. So these are not to scale. This is just to show you some of the diversity of moons that exist. If we have a look at some of the larger moons, there's some of them. There's the very hazy Titan right in the middle there, almost featureless because we really can't see what's going on, hence the idea of sending in Huygens on a parachute to tell us that yes, there are mountains and lakes and rivers there, and that's the idea of Dragonfly, to explore more of this world. Notice also just how big it is, much larger than our moon, for instance. But in the top there's been a lot of interest recently in what's going on with the moons of Jupiter, especially these three moons, Europa, Ganymede and Callisto. Io is volcanic because it's so close to Jupiter, but Europa and Ganymede and Callisto are collectively known as the icy moons of Jupiter. And these are very interesting. Even though their surface appears to be ice, we have good reason for believing that below the ice there are subsurface oceans. And there's probably more water on those moons than there is in all of the oceans on Earth. And if we know that life started in Earth's oceans and then came out of the oceans onto the land, then who knows what's going on in these oceans on these icy moons, under these icy moons' crusts. So that's why there's particular interest in these, and that's why the European Space Agency has sent the mission called JUICE, Jupiter's Icy Moons, and NASA has sent a sister mission called Europa Clipper. These are both on their way and will be getting to the Jupiter system in a few years' time. And they'll be having a closer look at these icy moons and hopefully trying to get a better idea of exactly what these oceans look like, how deep are these oceans, and what are in these oceans. Are there various dissolved minerals? Presumably, if there's rock down there, there will be dissolved minerals in the water as well. And if there are heat sources, and if there are water, liquid water, and if there are minerals, then we have all of what we think are the necessary elements for life to exist. So we won't be able to see life with these missions, but we'll at least take the first steps to establishing whether these ocean worlds are the right places for life to have evolved. I mentioned earlier that information was sent back from these missions by radio. Data is sent back using a large dish, as we can see here from the Cassini probe. There's a large radio dish which sends radio signals back to an even bigger radio dish on Earth. That's how information has been received from spacecraft exploring the solar system, well, essentially ever since we've been sending things into space. But relatively recently, an experiment has been done to see if there are alternatives. Rather than use radio waves, why don't we use lasers? Lasers can, in principle, have much higher data rates than radio transmissions. That's why those of us who've got broadband will quite likely have a fiber optic connection, because you can push much more information down a laser than you can a radio signal, simply because the frequencies are so much higher. So instead of having a large radio dish on Earth, you could have a modest sized telescope. And for the experiment that I'm about to describe, the Hale telescope in California was used. It's got a 5-meter mirror. Not all of the mirror was used. It was a relatively small mirror. This is small by the standard of the biggest telescopes in the world. But a laser was put onto a mission that was sent to the asteroid belt to see whether or not, as well as sending radio waves, whether it would be possible to send information on a laser beam. What information are you going to send back? Well, we want to prove that the data rates are high. So you don't want to just send an image. They decided to send a high-definition video transmission. What video are you going to send to test a laser? Well, they decided the video we're going to send is going to be a cat chasing a laser. What a great idea. So they sent this particular video, a high-definition video of a cat, Tatus the cat, chasing a laser beam. They sent this, and at a distance of 50 million kilometers, they managed to get a data rate of 260 megabits per second. That's faster than some people can get on their broadband from a server that's 10 miles down the road. Even when the spacecraft was 400 million kilometers away, they still got a data rate of 8 megabits per second. That's much faster than you can get with a radio signal, and so this paves the way for future spacecraft, perhaps, to have, as a matter of routine, lasers rather than radio transmitters, meaning we'll be able to get much higher data rates, and so we'd be able to get high-resolution images and high-resolution videos much faster than we can otherwise transmit over existing radio networks. So again, I've been telling you about a few different missions. Don't worry about making a note of any of these web addresses. I'll make these slides available to you offline. Bepi Colombo is on its way to going into orbit around Mercury, having gravity assists from the Earth and Venus and Mercury. On the right there, Cassini is no more. It's been crashed into Saturn. New Horizons, it's on its way out of the solar system. Juno is coming to the end of its life in orbit around Jupiter. And at the bottom there, we have the exploration of the icy moons from JUICE and Europa Clipper. So if you're interested in any of these missions, past, present, or future, then I suggest you visit these various agency web pages to find out more. Thank you all very much.